Welcome to this coding problem walkthrough. In this session, we'll tackle LeetCode problem number 803, titled Bricks Falling When Hit. This fascinating grid-based problem challenges us to determine how many bricks will fall after each hit. Stick around as we explore efficient approaches and break down the solution step by step. In this problem, we are working with a binary grid called grid, which has dimensions mxn. Each cell in this grid is either a 1, representing a brick, or a 0, representing an empty space. Now, the key concept here is stability. A brick is considered stable if either it is in the top row of the grid or it is connected to another stable brick through one of the four cardinal directions: up, down, left, or right. On the other hand, bricks that are not stable will fall if they lose their connection to the stable structure. Additionally, we are provided with a list of hits. Each hit specifies the position of a brick that will be removed from the grid. These removals happen one by one, and the grid updates after each hit. Our task is to return an array called result, where the kth entry in result tells us how many bricks fell as a result of the kth hit. Note that if no bricks fall after a particular hit, the corresponding entry in the result should be 0. The input for this problem consists of two components. First, we have grid, which is a 2D array of size mxn. Here, each element is either 0 or 1, where 0 denotes an empty space and 1 represents a brick. Second, we have hits, which is a 2D array of size qx2. Each element in hits specifies the I, j coordinates of a brick that will be removed. As for the output, we need to return an array called result. This array has a length equal to the number of hits, q, and each entry in result represents the number of bricks that fell after the corresponding hit was applied. To clarify these concepts, let's look at some examples. In the first example, the input grid is a 2D array with 2 rows and 4 columns. The grid is given as 1, 0, 0, 0, 1, 1, 1, 0. The hits array specifies 2 brick removals at positions 1, 0, and 0, 0. After processing the first hit at position 1, 0, the grid changes to 1, 0, 0, 0, 0, 1, 1, 0. Here, 2 bricks fall because they are no longer connected to the stable structure. Then, for the second hit at position 0, 0, the grid becomes 0, 0, 0, 0, 0, 1, 1, 0. In this case, no bricks fall because the remaining bricks are still stable. Thus, the output for this example is 2, 0. Now, let's consider a second example. Here, the input grid is 1, 0, 0, 1, 1, 1, 1, 1, and the hits are specified as 1, 1, and 1, 3. After the first hit at position 1, 1, the grid becomes 1, 0, 0, 1, 1, 0, 1, 1. In this case, no bricks fall because the remaining bricks are still stable. However, after the second hit at position 1, 3, the grid changes to 1, 0, 0, 1, 1, 0, 1, 0. Here, 4 bricks fall as they lose their connection to the stable structure. Therefore, the output for this example is 0, 4. To summarize the reasoning for the second example, after processing each hit, we observe the changes in the grid and the stability of the bricks. The first hit does not cause any bricks to fall, while the second hit results in multiple bricks losing their stability. This demonstrates how the number of falling bricks depends on the connectivity of the grid and the order in which the hits are applied. Understanding this example helps solidify the approach we'll need to take to solve the problem efficiently, especially for larger grids and longer hit sequences. Finally, let's review the problem constraints and edge cases. The grid dimensions m and n can range from 1 to 200. Each cell in the grid is either 0 or 1. The number of hits can be as large as 10⁻⁴, and each hit specifies a unique pair of coordinates within the grid. Some edge cases to consider include scenarios where all bricks are removed, leaving an empty grid, or cases with isolated bricks that fall immediately when hit. Additionally, there may be situations where no bricks fall after a hit because the remaining structure remains stable. With these constraints and edge cases in mind, our solution must be optimized to handle both large grids and a high number of hits efficiently. To solve the problem of determining how many bricks fall after each hit, we first need to understand the concept of stability in the grid. A brick is considered stable if it is connected to the top row, either directly or indirectly through other bricks. One approach to solving this problem is the brute force simulation method. Here, for each hit, we remove the brick in question and then evaluate the stability of every other brick in the grid. This is done by performing a breadth-first or depth-first search to identify which bricks remain connected to the top row. Once we identify the stable bricks, we can count how many bricks have fallen. However, this approach has significant drawbacks. Since we are performing stability checks for every hit, we repeatedly traverse the entire grid. This results in a time complexity of O, k times m times n, where k is the number of hits and m times n is the grid size. While straightforward to implement, this method becomes computationally expensive and inefficient, especially for larger grids or many hits. A more optimized solution leverages the union-find data structure, also known as disjoint set. This approach efficiently tracks connected components in the grid, with a focus on stability through connections to the top row. A key insight here is that stability can be analyzed more efficiently by reversing the hit process. Instead of simulating the removal of bricks repeatedly, we process the hits in reverse order, effectively adding the bricks back. Using union find, we can then connect bricks and track the sizes of these connected components. For each reversed hit, we check how many new bricks become stable by examining the size of the newly connected component. The union find operations, such as union and find, are optimized using techniques like path compression and union by size, making them highly efficient. This approach reduces the time complexity to O, m times n plus k times alpha of m times n, where alpha is the inverse Ackermann function, which grows extremely slowly. By avoiding redundant computations and leveraging the efficiency of the union find structure, this method handles large grids and numerous hits much more effectively. The union find approach was chosen for its balance of efficiency and clarity in solving this problem. Reversing the hits eliminates the need for repetitive stability checks, while the union find structure ensures connectivity management is optimized. The key insight that stability depends solely on connections to the top row allows us to simplify the problem significantly. By processing hits in reverse, we avoid unnecessary simulations, making this approach both elegant and computationally efficient. When comparing the two methods, the brute force approach, while simpler to implement, is computationally expensive and unsuitable for large-scale inputs. On the other hand, the union find approach, though slightly more complex to implement, excels in handling large grids and numerous hits efficiently. By utilizing path compression and union by size, the union find operations remain highly performant. Ultimately, the union find approach provides an optimal solution, achieving scalability and clarity while minimizing computational overhead. The problem we're tackling is LeetCode problem number 803, bricks falling when hit. Here, our goal is to determine how many bricks remain stable after each hit on a grid. A brick is considered stable if it is connected directly or indirectly to the top row of the grid. We are given a grid composed of ones, representing bricks, and zeros, representing empty spaces. When a series of hits is applied, bricks are removed, and we need to calculate how many lose stability and fall as a result. To solve this efficiently, we reverse the problem. Instead of removing bricks one by one and recalculating stability each time, we simulate the grid as though all the hits have already been applied, meaning all bricks in the hits list are initially removed. Then, we restore the bricks one at a time in reverse order of the hits, checking stability as we go. This avoids redundant recalculations. Next, we create a copy of the grid to mark bricks that are removed by hits. By setting the hit bricks to -1, we can distinguish them from cells that are naturally empty, which simplifies our computations later on. To efficiently manage stability and connectivity of bricks, we use a union-find data structure, also known as disjoint set union. This allows us to group bricks into connected components and perform connectivity checks quickly. A virtual roof node is introduced, representing the top row of the grid. All bricks in the top row are connected directly to this virtual node, simplifying stability checks. Now, we process the grid, with all hits already applied, to establish the initial connections between stable bricks. Bricks in the top row are connected to the roof node, while bricks in other rows are connected to adjacent bricks that are already stable. Stability is determined by direct or indirect connection to the roof. Once the initial setup is complete, we begin the reverse simulation. For each hit in reverse order, we restore the brick at the target cell if it was originally present. Then, we check if the restored brick connects to the roof or to any stable bricks nearby. If it does, we compute the size of the newly connected stable component. The number of bricks that fall as a result of this hit is equal to the size of this new stable component, minus the restored brick itself, and this is added to our result list. Finally, once all hits have been processed, we return a list of integers where each value corresponds to the number of bricks that fall as a result of a specific hit. This approach is highly efficient due to several key insights. First, reversing the problem avoids recalculating stability repeatedly, significantly reducing redundant computations. Second, the union-find data structure ensures that connectivity checks and merges are fast, with nearly constant time complexity for these operations. Third, the virtual roof node simplifies the process of determining stability, as any brick connected to this node is stable. To support the implementation, we use a few key data structures. The union-find structure tracks connected components of bricks, while a copy of the grid is used to manage bricks removed by hits. Lastly, the result list stores the number of bricks that fall after each hit, forming our final output. Analyzing the complexity of this algorithm, the time complexity is O, m*n plus k** log, m*n, where m and n are the grid dimensions and k is the number of hits. The first term accounts for processing the grid to establish initial connections, and the second term accounts for the reverse simulation using union-find operations. The space complexity is O, m*n, primarily for the union-find data structure. Several edge cases are important to consider. Hits on cells that are already empty, or on bricks that were previously removed, result in no bricks falling. Grids with no bricks at all will naturally produce a result of 0 for all hits. Additionally, isolated regions of bricks, which lack connection to the roof, will become unstable and fall when disconnected. These cases highlight the robustness of the algorithm in handling diverse scenarios. To understand how the algorithm works in practice, consider this example. The input grid is a 3x3 matrix, 1, 0, 1, 1, 1, 1, 0, 0, 1, and the hits are 1, 0, 2, 2, 0, 2. The output is 0, 3, 0. For the first hit at 1, 0, no bricks fall because the brick at this position is not connected to the roof. For the second hit at 2, 2, 3 bricks fall because this hit disconnects a stable component from the roof. For the third hit at 0, 2, no bricks fall because the brick at this position is already unstable. By reversing the process, the algorithm efficiently determines the result for each hit without recalculating stability repeatedly. This demonstrates the power of the union-find approach combined with the reverse simulation strategy. Here, we start by defining the structure of our solution. The hitBricks function takes two arguments, grid, which represents the brick layout, and hits, which lists the positions of bricks that are hit. We first determine the number of rows and columns in the grid, which will help us navigate through it. Next, we define the directions variable to represent the four possible movements right, down, left, and up for traversing neighboring cells. The index function converts a 2D grid position into a 1D representation for use in our union-find data structure. Then, the is_valid function ensures that a given row and column are within the grid boundaries. The DFS function performs a depth-first search to count the size of connected components. It starts by checking if the current cell is valid and contains a brick. If so, the brick is marked as visited by setting its value to 2, and the function recursively explores all its neighbors, summing up the total size of the connected component. Additionally, the is_connected_to_top function determines if a brick is connected to the top row, either directly or through other connected bricks. Finally, we define the union_find function, which initializes the union-find data structure that will help us manage and track connected components in the grid. Within the union_find function, we define the parent array, where each cell initially points to itself, and the size array, which tracks the size of each connected component. The find function implements path compression to locate the root of a given node efficiently. If a node's parent is not itself, we recursively update its parent to point directly to the root. The union function merges two components by attaching the smaller tree to the larger one, ensuring that the size of the larger tree is updated accordingly. This helps maintain an efficient union-find structure. The union_top function connects all bricks in the top row to a virtual top node, represented by the last index in the parent array. This ensures we can easily identify which bricks are stable and connected to the top of the grid. After defining these helper functions, we begin the first step of the algorithm, applying the hits. For each hit, we temporarily reduce the value of the targeted brick in the grid by 1, simulating its removal. This prepares the grid for analyzing which bricks remain stable after the hits. Next, we move to the second step, where we use depth-first search to connect all stable bricks. We iterate through the entire grid, and whenever we encounter a brick that remains unbroken and is connected to the top, we perform a DFS to mark all bricks in its connected component as stable. Following this, we proceed to the third and final step, reversing the hits and calculating the number of fallen bricks. By iterating through the hits in reverse order, we restore each brick that was hit by incrementing its value back to 1. If the restored brick is now connected to the top, we calculate the size of the connected component using DFS and subtract 1 to exclude the restored brick itself. This gives us the number of fallen bricks resulting from reconnecting the grid at that position. If the restored brick is not connected to the top, no additional bricks fall, and we append 0 to the results. Finally, we return the results in reverse order to match the sequence of the original hits. Here, we start by defining our solution class and setting up the basic framework for the problem. We begin by importing the necessary utilities and defining a constant for the 4 possible directions of movement: right, down, left, and up. The main method, hitBricks, takes the grid and the array of hits as inputs. First, we initialize the dimensions of the grid and an array to store the results of each hit. In step 1, we iterate through the hits to mark the bricks that will be broken by setting their value in the grid to 0. This ensures that the grid reflects the state after all hits. Then, in step 2, we establish connections between stable bricks using a union-find structure, starting with the bricks in the top row. These are directly connected to a virtual top node representing stability. This setup ensures we can efficiently track the stability of bricks as we process the hits. Now, we proceed to connect stable bricks for the rest of the grid. For each brick in the grid that remains intact, we check its neighbors to see if they are also stable. If the brick above or the brick to the left is stable, we use the union operation to connect them. This helps us build clusters of stable bricks, where each cluster can be thought of as a connected component. With this setup, we can later determine which bricks are stable and which are not. After setting up the union-find structure for the initial grid state, we move to step 3, where we reverse the order of hits. This allows us to simulate the process of adding the bricks back to the grid and calculating how many new bricks become stable as a result. Each time we reverse a hit, we first check if the brick was initially removed. If so, we temporarily restore it and calculate the size of the connected stable region before and after the restoration. When restoring a brick, we first connect it to any surrounding stable bricks by iterating through the 4 possible directions. For each neighboring cell, if the cell is within bounds and contains a brick, we use the union operation to connect it to the brick being restored. After updating the union-find structure, we calculate the size of the connected stable region at the top of the grid. By comparing the new size with the previous size, we determine how many bricks have become stable due to this restoration. The result for the current hit is the difference between these sizes, -1 for the brick we just restored, ensuring we only count additional bricks. Once all hits are processed in reverse order, we return the results array, which contains the number of bricks that fell for each hit in the original order. The union-find class is critical for efficiently tracking connected components in the grid. It uses 2 arrays, parent, which keeps track of each node's parent, and size, which stores the size of each component. The constructor initializes these arrays, setting each node as its own parent and the size of each component to 1. The find method is used to determine the root of a node's component, applying path compression to flatten the structure for faster future lookups. The union method connects 2 components by linking their roots. To ensure the structure remains balanced, the smaller component is always connected to the larger one. The size of the larger component is updated accordingly. This approach guarantees nearly constant time complexity for both union and find operations, which is essential for handling large grids efficiently. Finally, the getSize method in the union_find class returns the size of the component containing a given node. This is particularly useful for determining the size of the stable region connected to the virtual top node, which represents stability in the grid. With these methods, the union-find structure allows us to dynamically manage and query connected components in the grid as we process each hit. The entire solution is now complete, leveraging efficient data structures and algorithms to solve the problem of determining how many bricks fall after each hit. In this example, we start with a grid and a series of hits indicating which bricks will be removed. The first step is to apply these hits. For the hit at position 1, 0, we decrement the value at grid 1, 0 from 1 to 0, effectively removing the brick. Similarly, for the hit at position 2, 0, we remove the brick at grid 2, 0 by setting its value to 0. After applying both hits, the updated grid shows that the bricks at these positions have been removed, leaving the structure partially disconnected. Next, we identify the stable bricks after the hits. Stability is determined by bricks connected directly or indirectly to the top row. By performing a depth-first search starting from row 0, we mark all connected bricks as visited. Here, the brick at grid 0, 0 is marked as stable by updating its value to 2. However, no other bricks in the grid are connected to this stable structure, so they remain unchanged. Moving forward, we reverse the hits. First, we restore the brick at grid 2, 0, but find that it does not connect to the stable structure, so no additional bricks fall. We append 0 to the result. Then, we restore the brick at grid 1, 0, which does connect to the stable structure. This connection triggers a chain reaction, stabilizing bricks at grid 1, 1 and grid 1, 2. As a result, we calculate the number of fallen bricks as 3-1, which equals 2, and append this value to the results. After processing both hits, the final results for this example are 2, 0, indicating that 2 bricks fell after the first hit and none fell after the second. Now, let's examine an edge case where no bricks fall. In this case, the grid represents a different arrangement, and there is only one hit at position 2, 1. Applying this hit removes the brick at grid 2, 1, leaving the updated grid with a gap in the bottom row. This setup will help us explore how stability is evaluated when bricks are disconnected from the top. To identify stable bricks in the new grid, we perform a depth-first search starting from row 0. Beginning at grid 0, 0, we find that it connects to grid 1, 0 and grid 1, 1, so we mark all these bricks as stable by updating their values to 2. The remaining bricks, including the one that was hit, remain disconnected and are not part of the stable structure. When we reverse the hit, we restore the brick at grid 2, 1 to its original state. However, this restored brick does not connect to the top row or to any stable bricks, so no additional bricks fall as a result. We append 0 to the results. The final results for this edge case are 0, indicating that no bricks fell after the hit. In this final example, the grid consists of a single column of bricks, and the hits occur at the top 2 positions. First, we apply the hit at position 0, 0, removing the top brick and updating grid 0, 0 to 0. Then, we apply the hit at position 1, 0, removing the next brick and updating grid 1, 0 to 0. The updated grid now shows only one brick remaining at the bottom, disconnected from the top row. This setup will demonstrate how stability is affected when the entire top row is removed. Since no bricks remain connected to the top row after the hits, the grid remains unchanged in terms of stability. Now, reversing the hits, we start by restoring the brick at grid 1, 0. However, this brick does not connect to the top row, so no additional bricks fall, and we append 0 to the results. Next, we restore the brick at grid 0, 0, which reconnects all the bricks in the column to the top. Using depth-first search, we mark the bricks at grid 0, 0, grid 1, 0, and grid 2, 0 as stable. The number of fallen bricks is calculated as 3-1 equaling 2, and this value is added to the results. The final results for this example are 2, 0, indicating 2 bricks fell after the first hit and none fell after the second. To analyze the time complexity of our solution, we begin with the first step, marking hits. Here, we process the hits array, decrementing the corresponding grid cell for each hit. Since we process each hit exactly once, this step has a time complexity of O, k, where k represents the number of hits. Next, we move to the task of connecting stable bricks to the top row using depth-first search, or DFS. The DFS visits every cell at most one time, marking it as visited. In the worst-case scenario, where all cells in the grid are part of a single connected component, this step has a time complexity of O(m*(n), where m and n represent the grid's dimensions. Together, these two steps form the foundation of the algorithm's runtime analysis. When it comes to reversing hits and recalculating fallen bricks, the process involves iterating through the hits in reverse order. If a hit re-adds a brick that connects to the top, a DFS is triggered. While a single DFS can potentially visit a large group of connected cells, the key optimization here is that each cell is visited at most once throughout all hits. This means that, for all the hits combined, the total time spent on DFS is O(m*(n). Combining this with the earlier steps, we find that the overall time complexity for the algorithm is O(k) for processing hits, O(m*(n) for the initial DFS, and another O(m*(n) for reversing hits and recalculating. This results in a total time complexity of O(m*(n) plus k, which officially handles the problem within its constraints. For space complexity, the algorithm is designed with efficiency in mind. First, as the input grid is modified directly, no additional space is required for storing a separate grid. Next, the DFS operations rely on a recursive call stack. In the worst-case scenario, where all bricks form a single connected component, the depth of the stack can reach O(m*(n). Beyond this, the algorithm uses only a small amount of auxiliary space for variables such as directions and results, which are constant at O(1). If a union-find data structure were implemented, it would also require O(m*(n) space, but in this version of the solution, it's not explicitly included. Therefore, the space complexity is dominated by the DFS stack, resulting in an overall space complexity of O(m*(n). When comparing the optimized solution to a naive or brute force approach, the difference in efficiency becomes clear. A brute force method would involve recalculating the number of connected components after each hit, which means performing a full grid traversal and DFS for every hit. This leads to a significant time complexity of O(k*(m*(n), where k is the number of hits. The space complexity of the brute force method remains O(m*(n) due to the DFS stack. By contrast, the optimized solution avoids redundant work by ensuring each brick is visited only once across all hits. This reduces the time complexity to O(m*(n) plus k, which is a significant improvement, especially when the number of hits, k, is large relative to the grid size. The space complexity remains O(m*(n), which is optimal under the problem's constraints. The algorithm's behavior can be further understood by analyzing its best, average, and worst cases. In the best case, where there are no stable bricks, the DFS is never called, and the time complexity reduces to O(k), as we only process the hits. In the average case, each DFS explores a smaller subset of the grid, depending on the size of the connected components. While the exact time varies, the overall complexity remains O(m*(n) plus k. The worst case occurs when all bricks are interconnected, requiring each DFS to traverse the entire grid. Here, the time complexity reaches O(m*(n) plus k. Mathematically, this is justified by the fact that each cell in the grid is visited only once by the DFS, and with at most k hits, the total work is proportional to m*(n) plus k. The recursive stack depth is also bounded by the largest connected component's size, which is O(m*(n). Therefore, the final complexities are O(m*(n) plus k, for time and O(m*(n) for space. One common mistake to watch out for is neglecting how stability can propagate through connected bricks. A brick doesn't need to be directly attached to the top row to remain stable. As long as it's part of a connected component that links to the top, it won't fall. Make sure your algorithm identifies all such indirectly stable bricks. Another frequent issue is improperly handling grid updates after each hit. If the grid isn't restored correctly for subsequent hits, it can lead to cascading errors in your simulation. Additionally, using an inefficient union-find implementation can drastically slow down your solution. Techniques like path compression and union by rank are essential for keeping operations fast, even on larger grids. Finally, misinterpreting the problem criteria is a common pitfall. For example, bricks connected to the top row in any way remain stable, so it's important to avoid assuming that all adjacent bricks necessarily fall after a hit. Another critical detail is properly initializing the union find structure. If you forget to include the virtual top row, your stability checks will fail, as the algorithm won't correctly identify which bricks are connected to the top. Now, let's consider some important interview insights. The key idea in this problem is to leverage union find to dynamically track connected components and their stability. This approach is efficient because union find operations, like union and find, are almost constant time when optimized. It's also a great way to demonstrate your understanding of dynamic connectivity, especially with extensions like virtual nodes. You should be ready to explain why union find is ideal compared to alternatives like DFS or BFS. While DFS or BFS can also track connectivity, they're slower, especially on larger grids, making union find the better choice. When solving this problem, be prepared to handle a variety of edge cases. For example, some hits might not affect any bricks at all, while others could cause all bricks to fall. You might also encounter scenarios where the grid is empty or has no removable bricks, so it's important to account for these possibilities in your implementation. Additionally, this problem shares similarities with several related problems. For instance, LeetCode number 200, number of islands, also involves identifying connected components, though it focuses on counting them rather than determining stability. LeetCode number 305, number of islands 2, is another dynamic connectivity problem where land is added dynamically, much like handling hits in this problem. Similarly, LeetCode number 547, number of provinces, and LeetCode number 684, redundant connection, both use union find to solve graph-based connectivity problems, showcasing the versatility of this approach. There are some alternative approaches worth discussing. One option is to use DFS or BFS to find all connected bricks and their stability after each hit. While this method works, it's less efficient, with a time complexity of O(n) squared per hit, which can lead to timeouts on larger grids. Another method is brute force simulation, where you remove a brick for each hit and simulate gravity to determine which bricks fall. However, this approach is even less efficient, with a time complexity of O(n) cubed, in the worst case, and is generally unsuitable for interviews. A more practical alternative is to optimize the union find approach further. By pre-computing stable bricks and incorporating a virtual top node, you can streamline initialization and improve overall performance. This strikes a good balance between clarity and efficiency, making it one of the best solutions for this problem. Great work! In this session, we tackled the bricks falling when hit problem using an efficient union find approach to solve for grid connectivity. We reviewed key concepts, including time and space complexity considerations, and explored why this method is optimal. Be sure to revisit similar problems to strengthen your understanding. Thanks for tuning in, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!